What's up, Coder Byte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and this week we have another wonderful system design question for all of you. That's right, we are designing Dropbox this week. Now, when I was doing the research for this video, I found a ton of resources out there that were mostly just kind of talking about the high-level components of Dropbox. I think Dropbox as a concept is pretty simple. You have a bunch of files on your machine, you want to access them anywhere. They go to the cloud, and you should be able to add and remove and share and blah, blah, blah. Everyone knows how Dropbox works. But I think actually under the hood, it's a very complex system. There are so many different avenues that you can go down with your interviewer and talk about the different pieces of the system and how you might design them. So for this video, I actually wanted to kind of dive deep and go into some of those components because I think that in an interview, it's those small different, there are always those kind of little nuggets of gold that you can drop as the person being interviewed to show your expertise to your interviewer. And I think that this is a wonderful opportunity to collect some of those nuggets and keep them in your toolbox so that when you go to those interviews, you can kind of impress and really just show your mastery over some of these very basic concepts. So let's get into it. I hope you guys enjoy this as much as I enjoyed researching this topic. I actually found a ton of resources from Dropbox themselves, and I love when a company puts out content about their systems because in my mind, that makes the product that much more valuable when you can understand it. So yeah, let's do this. This is going to be the first part of a two-part mini series all about Dropbox. And put your thinking caps on because we're going to be thinking. Let's go. The problem. Design a system such as Dropbox or Google Docs in which a user can store their data on remote servers in the cloud. The remote servers should store files durably and securely, and these files should be accessible anywhere with an internet connection. The user should be able to make changes to files locally and have the changes be automatically reflected in the cloud and on other clients. Okay, so I think everybody here understands, if they haven't used Dropbox, they understand the concept behind Dropbox. It's hard to imagine that once upon a time this was a really novel concept, right? That like people didn't just have access to a tool like Dropbox or Google Docs, but once upon a time this was a very new thing and a very valuable thing. So let's recap a little bit, our system design toolkit and how we want to approach any system design problem. So system design recap. The first thing you want to do always is to scope the problem, right? And that just kind of is your opportunity as the interviewee to interview your interviewer about the problem. This is where you ask them the questions all about the system and you find out what are the key components I have to think about, what are the use cases, stuff like that. So in this case, I think, again, we all know how Dropbox works and what it's supposed to be accomplishing, but that's where you kind of reiterate and confirm with your interviewer exactly the direction in which you should be taking the problem. The second thing we're going to do is capacity estimation. This is all about, storage sizes, traffic estimates, the kinds of like numbers, right? The numbers behind the system so that you can anticipate what kind of load the system should be able to handle in various ways. The third part, I think, is, and I think these steps can kind of come in different orders depending on the problem. But the third / next step might be database design, right? You're thinking about how am I going to store my data so that my system can use it appropriately? And this takes into account, of course, steps 1 and step 2, because you're going to design your database based on different capacity estimations that you've made and the problem you're trying to solve. The fourth step, and again, these are kind of, you can do these steps together separately in different orders, but this is kind of the next area in which you want to discuss with your interview. This is the system APIs that you want to discuss. These are I always think of an API almost as an agreement between the different components of the system. How are the different components of the system interacting with each other, communicating with each other? What are the expectations in terms of how those communications happen and what happens after those communications? This is where you'll do your components, the different kinds of components in your system, and you'll sort of begin to lay out the broad map of all of the different pieces of the system and how they interact with each other. And then finally, or not finally, and then you'll do your core algorithm. So in this case, the core algorithm might be the syncing between your local file system and the remote file system, or the way in which the files are saved. How does it get from my machine to the remote cloud? That sort of thing. And this is, again, you won't do all of, most big, large systems have many core algorithms. So this is an opportunity for you to ask your interviewer, what direction are we going with this? Because you likely won't have a lot of time. So you'll want to kind of pick the core algorithm that you would like to choose to demonstrate something to your interviewer, or you can kind of gauge from what they're asking, where do they want you to take this problem? And now, finally, we do our load balancing and caching. This is, I always say, probably your last step. This is where you'll want to actually take the design that you've designed, and you'll want to add in the load balancing and caching that you might be able to, conveniently put in different aspects of the system to make it very scalable and very, help make your system more available to more people. I always say this is a good last step, because if you have a good core, if you've done everything else right, it becomes obvious where you can kind of appropriately place a load balancer or a caching layer or whatever, especially because you already understand the capacity estimation and scoping the problem. You know exactly what the system is going to require in terms of load balancing and caching. So if you've done your job well at this stage, it should be it's the next logical step for you to just put it in and make it so that it's an actually robust system to be used. So I want to talk this week. Last week we did a more simple example, right? We did the URL shortening system, bit.ly or tiny URL. And this week I want to really focus on these two pieces, the database design and the system APIs. Again, these are the major components of our system. The rest of it is important in an interview, but this is where the actual kind of meat of the algorithm comes from, right? This is going to be what actually makes the system. And so I'm going to focus on this more or less in the next two videos. We're going to do a deep dive on the database design today and the system APIs and the components of our system. And next week, we will focus on some other components of the system and maybe some core algorithms as well. Okay, so number one, scope the problem. What are some feature requirements for Dropbox? Our first feature requirement is that it stores files durably and securely. So what does durably mean? Generally, when I hear the word durably, I think of that it has to be accurate and it can't just disappear. If I have a file on my system and I'm assuming that my Dropbox is going to sync it, I am going to expect that that is actually synced, that the file got saved, and it not only got saved, but is now accessible from other devices. So that's what I think of when I think of durably. It's durable, it's not half the file, it's not an old version of the file, it's the file and it's everywhere. Securely, I think, is obvious that, not anybody can just take my file, etc. Okay, so we want to be able to upload, update, delete, and download. Again, I think pretty self-explanatory with Dropbox. Our next system requirement is that we need to be able to have some sense of file history and versioning. So that if I have I've updated a file or, changed it in any way, there's a concept of remembering what it used to be compared to what it looks like now. Also, the file and folder sync, it has to sync across multiple devices from anywhere with an internet connection. That is a very important piece of this, and we're going to talk about this more next week. But this is that if I have updated a file on my file system locally, I expect that if I log into my Dropbox from my friend's computer, that it will also be there and I can just download it and use it there as well. Not only can I download it and use it there, but I can update it and then I'll have it back on my local machine as well. This is a very key point of Dropbox. I think it's the thing that makes it very valuable. And so again, we'll talk about this more in the coming video, but this is a pretty important piece of this system. Users should also be able to share files and folders with other users. I want to be able to give my mom a link to one of my folders in Dropbox and have her be able to download whatever's in that folder. That's something that is, again, a pretty key component of the Dropbox system, that we should be able to not only share it among our user, but also share it with other users on the system as well. And finally, the system should support offline editing, that users should be able to add, delete, modify files offline. And once they come online, changes should be synchronized to the remote server and other online devices. So if I'm in a random coffee shop and I'm working on my novel, I want to make sure that the next time I have internet, my Dropbox is going to pick up on those changes, despite the fact that it was not connected to the internet when I was working on my novel at that random coffee shop with no internet. This is another key component of Dropbox. Okay, so I want to talk now about some of the unique aspects of the Dropbox system. These are some of the things that are it's what makes Dropbox Dropbox, and it's the things we really can't compromise on. And I think these are going to be guiding lights for our component design. There might be many ways to solve a problem, but if we don't kind of figure out that these are specific to Dropbox and we need to make sure that we're checking all of these boxes when we create our components and our actual system design. And we want to make sure that we are not sacrificing in these areas. I think this is a very useful exercise in any system design question, because it can kind of help you give you some guideposts or some, the frame of your framework, if that makes sense. So for Dropbox, I think this is a unique aspect for Dropbox. It's not something you see every day. There's a very high write volume, right? Most systems, when there's this concept of reading and writing data, most systems, the ratio is always that the writes are much lower than the reads. Most people are getting data and reading it rather than creating data or uploading it. That is not the case with Dropbox. And this is a unique aspect of the Dropbox system, that its users are creating and writing to the database almost as frequently as they are reading from the database, which is difficult to optimize for, because often you have to optimize for one or the other. It's not so easy to optimize for both. And so we'll talk about this more in the database design portion of this video, but this is something to keep in mind as we kind of go forward, that in this system particularly, we're going to have a lot of writes, almost as many reads, right? It's going to be a 1-to-1 read to write ratio. So this is another unique aspect of the Dropbox system. It's not so unique, not as unique as the read to write ratio, but it's important to kind of be aware of at the onset. We have some acidity requirements. We can't be wrong about the data. Dropbox would be entirely not as useful if we, for example, sometimes we wrote stuff and it didn't get saved. Okay, 90% of the time it gets saved. No. When you write stuff to a file, you want it to accurately be saved and synced. So what is ACID? In case you don't know, or in case you need a refresher, because anytime I hear anything about ACID, I need a refresher. So let's go through it. It stands for, it's ACID, and each letter stands for something. So the first letter A stands for atomicity. Atomicity. I got to do like what is that called when you do like a bloopers reel? One day I'll do a bloopers reel for you all. Atomicity guarantees that each transaction is treated as a single unit, which either succeeds completely or fails completely. So this means that if I'm updating a file, and some part of the update fails, we throw away the whole thing. We don't save some of it because that is inherently, it's like dishonest, right? This is not something like, I'm trying to think of like, if any of you have heard of the internet protocol UDP or WebSockets, where it's kind of, you're just throwing stuff at an open port and there's no guarantee that you're going to get all of the information. As long as you get most of the information, it's good enough. This is often used for video streaming, right? Because our computers are so, you know, they're very good at what they do. And in a video stream, if you get most of the data, it's good enough. There might be a skip, there might be a lag, but it's good enough. So we can't have that with Dropbox. We need to be able to have the whole file and all of the saves, or if we mess something up at some point, we have to throw the whole update away because we have to have a sense of the file being durable, right? It's saved, it's accurate, it is what it is. Okay, C, consistency. Any data written to the database must be valid according to all defined rules. So a lot of people talk about, when they talk about the C in ACID consistency, they talk about, database triggers or any sort of, waterfall operations that when you save something, something else is happening at the same time, right? So a trigger might be that you have a history table that's keeping track of something that's happening in a different table. And for the data to be consistent, we need it to actually, like, all of the rules have to happen. And if all of the rules have to happen, then if some of the rules don't happen, then none of, right? How awful would that be if sometimes you got history, sometimes you didn't? Or let's say there were two triggers and only one of them happened. So that's not a very consistent system, right? Okay, next up we have I, isolation. Ensures that the concurrent execution of transactions leaves the database in the same state that would have been obtained if the transactions were executed sequentially. So this basically means that anything that's happening concurrently, and concurrently, if you don't know, means at the same time. This is a huge concept in computer science, that it's the same if those transactions were executed sequentially. You can kind of think of this as like a Redux store. I don't know if any of you, work with React or Redux or any sort of state management system. Heads up, we're probably going to be doing a little React course for you all, so get excited for that. You want to be sure that the reduction of all of the things that are happening, it always kind of results in the same thing, whether it's happening at the same time or sequentially. So with database, any sort of database concept, we want to be sure that any of the transactions, the database is going to look the same, whether it happens sequentially or concurrently. So if I make a file change to a file, obviously, if I make a different file change at a later date, that's going to change the state of the database, and it has to maintain that ordering. The nature of the sequential ordering matters. But if something is happening in one transaction, it's assumed that it's going to kind of result in the same reduction of all of those transactions, whether they happen concurrently or if they happen sequentially. So I don't know if that makes sense. I hope that makes sense. And finally, we have the D, durability. We keep mentioning this word. This guarantees that once a transaction has been committed, it will remain committed, even in the case of a system failure. So let's say we commit something to the database and then the database server dies, it goes down. We want to be sure that just because it died doesn't mean that transaction got lost. We have some sense that even if the server goes down, we have some replication, we have some way of determining that all of that data is safe. And when we bring it back up or we, start a new instance of the database, we have a way of taking all of that because it was committed and it's going to remain committed and be in the data. So all of this, what does this have to do with our problem? Because we have such an important acidity requirement for this system design, this leads us to probably have to use a database with strong acid properties. So in this case, we want to use a database that will actually it will score high on all of these things. So in general, you need strong ACID properties, you want to use a relational database like MySQL or Postgres. All of those databases have a lot of this stuff built into them. You don't have to manage this as the user or as the developer who's using the database. When you're using a database like MySQL or Postgres, you can use the database and assume that it will have a lot of compliance with all this sort of thing. So that's why I'm talking about this. This is definitely not the case to use, like, let's say DynamoDB or some, Mongo or whatever. And that is a very important piece here, because if, let's say, you decided to use one of those non-relational databases as your database layer, I think your interviewer would not really like that, because it kind of defeats the purpose of the entire agreement between Dropbox and its users. You have to make sure that it scores high on all of these properties. And so again, this is going to determine what kind of database are we going to use here. Great. Okay. Capacity estimates. So these are just some random capacity estimates. I kind of took this from Dropbox themselves and from some other videos, approximately what kind of, their numbers are for their users. Again, the tip here is use numbers that are easy to multiply and kind of use between. You don't want to be in an interview and get something wrong that's like doesn't even matter, right? Don't do that. Make sure if you're getting something wrong, it was a difficult part of the problem, not because your multiplication was difficult. So for us, for Dropbox, approximately we have a total number of users of 500 million. We have a total number of daily active users, approximately 100 million. We have the average number of files stored by each user is about 200. The average size of each file is approximately 100 KB. The total number of active connections per minute is 1 million. Now, this is going to come into play when we talk about the way in which we have our clients interacting with the remote servers, right? Because this is something that's going to be very important to the Dropbox system. How many connections, aka how many local computers or clients, are actually connected to all of our remote servers at once? Because that really matters. We're going to have to really talk about that when it talks about load balancing and syncing everything. We need to kind of know there's a lot of active connections per minute, and we're going to have to plan for that. So we'll talk about that more in the coming slides. But keep in mind, for now, approximately, we need to be able to have 1 million active connections per minute. Okay, so let's talk about total number of files in our system. So total number of files is going to be our total number of users times the average number of files stored by each user. So that's 500 million times 200, which is about 100 billion. And the total number of storage required is going to be 100 billion, which is the total number of files, times the approximate size of each file, which is 100 KB. So that's going to be approximately 10 PB, which I think is petabytes. Okay, so let's talk about our high-level component overview. I took a lot of this from a great video that I believe the head of all of the server architecture at Dropbox, he gave a lecture at Stanford all about the iterative nature of how they design Dropbox. And I thought that this is a really good thing to talk about, because it's very important in your interview, right, to not get afraid. Often in an interview, you're like, I don't know, I can't do it. And I think that it's a really, really important skill to be able to, do what you do know. Do something easy at first and then iterate on that, because that in and of itself is impressive to an interviewer. I find it impressive when I interview someone if they can kind of start small and then grow from there. Okay, your initial design doesn't work for 1 million users, but that's fine, because most startups don't have 1 million users at the beginning. And I think that was a really valuable point that I got from that video, which is even a company like Dropbox, which at the moment, scaling Dropbox is a huge, huge undertaking. And the way they started was not scalable. They had to iterate on that. And I think that once you iterate, it also offers you the opportunity to build slowly, right? And it's like, Well, I don't know how to get to all the way to where I'm going, but I know where to start. And then you can kind of build from there. So really lean into that. So I'm going to kind of briefly talk through, this is legitimate. I took this from that talk. This is how Dropbox scaled. And they said, from their 1 employee, 2 employees to their, 100 employees or whatever. Um, and this is how they iterated. This is how they built it slowly. And it also allows for opportunity to discuss why and how you would iterate depending on different scenarios. So the first way that they started is actually very simple. Of course, they had their clients and they had their one server, mono server, God, except, server. Um, and the clients just talked to the server, and the server held everything. It held all the files, it held all of the, routing, it held all of the subscription information, the user information, and the clients just talked back and forth between the server, and it was fine. It worked for a little while, right? And this little line is just the boundary, right? It's the boundary between the clients and the servers. So don't get confused by that. Obviously, this quickly did not work so well, so they iterated. And the next way they stored everything is they split some stuff out, right? So then they started to have a server, and the server was accessing different things in different places. So the server, the actual user's files were being stored in S3, which is an AWS concept. If you haven't heard of it, it stands for simple, what does it stand for? I don't know what it stands for. Simple file storage. That's not what it stands for because that's not 3S's. But anyway, they put all of the users' files in S3 and AWS, and then everything else they stored in a database that was at least not on the same machine as the server, right? They split the boxes a little bit. And then the clients communicated only with the server, but the server was able to kind of pull from the database and then from S3 and give things back to the clients. So that was their next iterative design. Then finally, this is going to be the more complicated one, that kind of looks a little bit more about what it looks like now. They had this concept of, first of all, the clients, and then they also had these concepts of these 3 different kinds of servers. They had a meta server, a not server, and the not server is just a short way of saying like notification server, and the block server. And we're going to talk about each of these in depth, but just to give you a little bit of a brief overview here, essentially what was happening was in this design, right? So in this design, this server was overwhelmed very easily because, as we said in our capacity estimates, the clients had to have a lot of open connections at any given point to the server. And so for the server to be maintaining those connections and also not only be available for asking for things, for writing things, and also letting the clients know that there have been changes that were made, it's a lot of connections for one server to handle. So the way they kind of split that up is that instead, you'll see, instead of any of these servers having 2 bidirectional arrows, they kind of made it so that the clients are only ever talking to this meta server. And the meta server is the thing that gets the metadata about the files. Now, what is the metadata about the files? The metadata about the files is, what are the files? Who do they belong to? Where are they? And there's this concept of a block server, because to always be saving and reading and writing full files is very expensive. If I have a file that's 1 gig and I change 1 line, and every single time I change 1 line, I'm giving and taking, reading and writing 1 gig of data, that's going to get very costly very quickly for no really good reason. So the block server kind of chunks things, right? It makes the files into different blocks so that if you only change a line, you're actually only ever talking about that block of the server. So the 2 places that the client talked to is now this meta server and this block server. So let's say I'm updating a line in my file. I might send to the block server that I updated that block. That gets saved in S3 as the actual file. And then it goes and talks to this metadata DB, because the metadata DB now needs to know that there's a new block that's part of this file. and that old block is no longer valid. So the metadata, server and DB, is what's keeping track of the different blocks or chunks of the file, and also who they belong to, and a bunch of, the size, whatever, all of the metadata about a file. So the client is only ever sending things to either of those servers. Now, what happens to the rest of the clients that now need to know about these changes? Because remember, part of Dropbox is that I need to have all of my files in all of my clients, on my computer here, at my computer at work, at my phone in, wherever, my friend's computer, etc. So what then happens is the meta server will send a notification to the not server, which will say, hey, something changed. There's something new. And then it's the not server that then sends things back to the clients and kind of propagates the change out and says, there's a new change, download it. And in that way, they vastly change the traffic on each of the servers, because now most of the servers only have one job, and it's also unidirectional, right? There's only ever listening or sending. And I think that that was a really key part of the, Dropbox design when they split things out in this way. Okay, so let's talk a little bit about the client, because I think the client is, each of these components you could make an entire video about, of course. But for this video, I want to talk about the clients, and we're going to talk about the database design. So let's talk about the clients. So here's our little, I want to keep this here so that you guys can retain the broad level picture of what's happening. But I'm going to show you a little bit about what's happening on the client and how things are broken up there. So here is our client. And essentially, our client is, of course, also very complex. And this is the thing that's running on your local machine on Dropbox. And there are a few different parts of it. There's the chunker, which is just briefly, it's the thing that chunks the files. There's the watcher, it's the thing that's watching your Dropbox folder and seeing if there's changes. There's the indexer, which is keeping track of what's being watched in the chunks. There's the client metadata database, which is basically similar to the remote metadata database. And these are the things that are keeping track of the files. They kind of mirror each other, all of the information about the files and the chunks and how they relate to each other. And then there's the synchronizer. There's the thing that actually takes what you have locally and syncs it with whatever is on the remote machine. So let's talk about each of these components in depth. So here we again have kind of the client broken up into these subcomponents. So first, let's talk about the chunker. The chunker splits the big files into chunks. This also reconstructs the original file from the chunks. So this is what we were talking about before, right? If you have 1 gigabyte file and you only change a line, you actually only really want to send the line or a chunk, right? A small chunk of the file, so that we can avoid needless bandwidth, sending giant things that only actually haven't really changed much. We don't have to change everything to change one small piece of the file. So that's the chunker's job. The chunker's job is to split things into chunks. We then have the watcher. The watcher monitors the files for file changes in the workspace, like any updates, creates, deletes, etc. And then it notifies the indexer about the changes. So the watcher is really just, again, it's what it sounds like. It's watching your file system, because a key component of Dropbox is that you don't have to sync it like it syncs automatically. You don't have to tell it, hey, I changed something. We then have the indexer. So what's the point of the indexer? The indexer is listening for the events from the watcher. So it's saying, hey, something changed, right? Something changed, a chunk changed in this file. And it updates the client metadata database with information about the chunks of the modified file. So it saves it locally, saying, hey, one of the chunks changed. It looks different, or it's in a different place, or whatever. It also notifies the synchronizer after committing the changes to the client metadata database. So this is the thing that tells the synchronizer, hey, we changed something. Go tell the remote servers that something changed, because what's the point if all of this is happening and it's not reflected on the other computers that you want your files on? And then finally, we have the synchronizer, which is listening for events from the indexer and communicating with the meta service or meta server, and the block service or the block server for updating the metadata and modified chunk of the file on the remote servers. So this is the thing that's actually reflecting the changes in the cloud. So this is managing that your machine looks the same as the machine that's mirrored in the cloud infrastructure of Dropbox, so you can get it on all of your other devices. It also is listening for changes broadcasted by the notification service. That's that not server, right? And downloads the modified chunks from the remote server. Because it's not a one-directional data flow, this is something that also, if something changed on someone else's computer or your other computer, you get that as well. So if there's a notification from the not server that says, hey, something got changed on another system, this is where it gets downloaded and incorporated into your local file system. And then finally, the client metadata database. This is storing the information about the different files in the workspace, like file chunks, chunk version, file location, the file system. This is kind of the thing that puts it all together, because if we have just chunks with no concept of what the chunk belongs to, it's not as valuable, right? So we have to have a way of putting together all of the chunks to make our actual files. So that's kind of a brief overview of how the client works on Dropbox. Let's talk about this meta server. So this is the meta server that's in the cloud. This is the thing that is kind of, again, it's taking that all of the meta information and it's storing all of the details about the files. So this is the meta server. It's responsible for synchronizing the file metadata from client to server. So this is the thing that the synchronizer is talking to. It's responsible to figure out the change sets for different clients and broadcast it to them using the notification service. So this is the thing that's like, oh, you changed something on your machine and I don't have it, then I better send it to everybody else, right? So this is the thing that's talking to the not server, which will then talk back to the clients about any changes that have happened. When a client comes online, it immediately pings the meta server for an update. The meta server determines the change set for that client by querying the metadata database and returns the change set. So this is the part where there is that idea of I want things to be reflected even if I'm editing things offline. So that when I come online, I know that I'm going to download the change sets that anybody else has made and also upload my own change sets that I have made. If a client updates a file, the meta server again determines the change set for other clients watching that file and broadcasts the change set via the notification service. So this is saying more of the same thing, right? This is just if a client updates the file, the meta server talks to the not server, which then sends a notification and it propagates downwards. And the meta server is, of course, backed by metadata DB. So this is not just a server, there's also a database, and the database contains the metadata of the file, like the name, the type, is it a file or a folder, the sharing permissions, the chunk information, etc. So we're going to go deeply into the metadata database, and we're going to talk about how Dropbox has actually changed their metadata database in order to scale. So I think that's going to be really valuable and useful, but we'll do that in a few slides. But basically the server is more, it's reading and writing, it's figuring stuff out, it's determining those change sets. And of course, this is all persisted in a database. Okay, let's briefly talk about the block server. So this is the part that is actually, chunking the files and saving the file content, the actual content of the user's files. So the block server. It interacts with block storage in S3 for uploading and downloading files. So this is the thing it's not just saving about the file, it's saving the actual contents of the file. Now, I didn't talk about this at all here, but just in case you're curious, there's this idea in Dropbox of deduping. If I upload a song and someone else uploads the same song, actually in Dropbox's kind of infrastructure, that song is only uploaded once, and then it's shared among the users, which is kind of interesting. But of course, when they scaled, they had to do this. They can't just Just because 100 people save the same thing does not at all mean that they want to save 100 versions of the same thing. So the block server and S3, that's kind of where all that magic happens. The clients connect with the block server to upload or download file chunks. When a client finishes downloading a file, the block service notifies the meta server to update the metadata. When a client uploads a file, the block server notifies the meta server to update the metadata corresponding to this client and broadcast the messages for other clients. So again, the block server is also interacting with the meta server and the metadata database so that when there are new or different chunks, the metadata of the file is adequately or accurately updated so that it can go to the not server notification service and then propagate to all the other clients. So again, this is a pretty complex system, but if you take apart bit by bit what's happening, you can kind of see that there are kind of simple rules here that allows for this separation of concerns. And again, I want to stress that what's really cool about the way they've designed this and the way you should think about if you're designing this is kind of the direction of the data flow, that every component kind of has one job and it sort of all works together, but it allows for massive scalability so that no system gets overwhelmed at any one point. So let's talk about this not server. So this is basically the thing that then is sending the notifications to all of the clients after there are changes. So I added in a little component here that I haven't had in other slides, which is just a queue, because this is, again, an opportunity to kind of talk through, you don't want to lose any data. You don't want the meta server to ever be talking to the not server and lose a request. You want to actually add it to a queue to make sure that everything gets processed, because we want all of our clients to have the updates. Because if you get a file that's not the most updated version, it defeats the purpose of Dropbox. So that's a very important piece of this system. So the not server. It broadcasts the file changes to connected clients, making sure any change to the file is reflected all watching clients instantly so that everybody gets it. Everybody gets the changes. Now, this is an interesting piece. This is implemented using HTTP long polling. What does that mean? The server keeps the connection hanging until the data is available for the client. Once the data is available, the server sends the data, closing the connection. Generally, for each long poll request, there is a timeout associated with it, and the client must establish a new connection post-timeout. So what does this mean? This essentially means that there are open connections between the not servers and the clients at any given point, and they're always waiting for data because probably there's going to be data coming down. And when that data comes down, it closes the connection and then reestablishes a connection. Rather than the not server trying to kind of create and close connections at will, it keeps them open because it knows that its only job is to send these notifications. So it's ready at any given point, and that's what helps make it instantaneous and help the actual changes be propagated almost instantly and also reliably. And this is only able to be done because they moved this whole, piece of the system to its own server. This server, its only job is to talk to the clients. So remember those 1 million connections per minute? That is, the not server is entirely, built with that in mind, being able to have that be reliable and have that be scalable. So there's a queue between the not server and the meta server, which provides an asynchronous medium of communication between the meta service and the not service. So what does that mean? It's asynchronous, meaning that the meta server can add things to the queue and the not server can pull things off the queue as it's ready, rather than the meta server always relying on the not server hearing everything it's saying. And this allows for, again, this decoupling. They're not reliant on each other. which is always very scalable. It's always good to kind of decouple things so that things are not relying on the other thing being listening for me to be talking to it. The not service can keep consuming the messages at its own pace without affecting the performance of the meta service. This decoupling allows us to scale both services independently. So what that means is if the meta server is overwhelmed or the not server is overwhelmed, it doesn't affect each other. There's no data loss because they're both reading and writing from a queue. And the queue retains things until things get pulled off the queue. So again, this is a very useful tool for decoupling and for allowing different parts of the, entire architecture to scale independently and not have one part of the system get overwhelmed and bring the whole system down. So that was a pretty brief overview, but also a lot of information and a lot of words in the slides, I'm sorry. But I hope that sort of paints a picture of how you can go about designing a system like Dropbox and iterate on the design to better control for different aspects of the system that you want to control for. Okay, so I want to talk about this database design. And I think this is like edges on core algorithm and also database design. I think this is kind of when you're working on something with scale, it's often when you're working on something where it's not scaled, these details don't matter as much. But when you're at a bigger company that actually scales, often there's so much value that you can have if you have a good database design. And I'm a back-end engineer more or less. I always find it very impressive when a candidate knows databases pretty well, because it's one of those things that, again, if you've only ever done side projects, it doesn't really matter. But if you've worked at a big company or a, small company, these are kind of the things that they can give you huge performance wins. And it's kind of like easy wins, right? It's the database is doing a lot of the heavy lifting, so you as the developer don't have to. So I wanted to really kind of dive into this and talk about the way in which the database was designed in Dropbox in order to scale and to, accommodate certain requirements. So we're going to talk about that metadata DB. Remember, this is the thing that's keeping track of the information about the files. And we're going to talk about a specific table called the server file journal. This is going to be a log of everything that has happened to a file. So this is kind of like a history record, if you can imagine that. So the first way they created this, and this is MySQL, in case someone doesn't recognize the syntax, is that they created a table called server file journal. And essentially it had a primary key of ID, a file name. This is all pretty standard. They had a latest, which was a tiny int. So this is just almost like a Boolean byte that's either turned on or off. Is this the latest file or not? And then they had this NSID. And NSID was the namespace ID, which is like, let's say you might have a namespace that is your user's folder, or shared, let's say you have a folder that you share with your mom that has a namespace associated with it. Because what does that have to do with anything? The namespace is the thing that's being synced, right? You don't sync your namespace with someone else's namespace, but any client with the same namespace on it has to be synced. So that's kind of what that NSID is, and etc. There were a few other things on the table. So the first thing that happened is that they added, the first iteration is that they added this concept of a prev-rev, or a previous revision, maybe. I don't know what that stands for. Reference, but that's with an F. I don't know. And this was, you can see it's an int 10, which is the same as the ID, int 10. And it's essentially just a pointer to the last, right? It's the last known version of the file. So that any file server file journal, you can kind of create a linked list back to what was the last one, what was the last one, what was the last one. So that was the first thing they did. The next iteration that they did is, instead of just using the ID as a primary key, They changed the ID to a composite primary key, which is using more than one field for the ID. And what did they choose? They chose the NSID and latest and ID. So now the primary key is these three fields. And what that accomplished is that the entire table was then ordered by the namespace and the latest, right? And the ID. So that instead of having to look through the entire table when you're looking for a file and the latest file, right? You'd have to first get the whole table, then look for the latest version of the file, then look for the, or you might look for all of the files in a namespace, then look for the latest version of the file. Now, it's all already ordered that way. So you can already assume that all of the files with NSID of the same are together. And then the one file that is the latest is at the top. And then it's ordered by ID, right? The primary key is an implicit ordering. So as things are added, you can almost use the ID as a timestamp. It's not an actual timestamp, but you can imagine that if I added something with the ID of 1 and then 2 and then 3, you know that the thing that has the ID of 3 is happened after the thing that has the ID of 2. So that's kind of how that worked. And they were really able to very easily, relatively easily, have this be much significantly faster just by virtue of changing the primary key from just ID to this composite ID. The next thing that they did is they removed latest. Now, why did they remove latest? They removed latest because this was an interesting thing. Having latest there makes it much more efficient for reading, right? Because at a glance, you have the latest thing and it's at the top, right? But for writing, which remember, Dropbox is a very write-heavy database, every time you write to this table, you then have to shuffle things around. You have to shuffle around that the latest thing is no longer the latest thing, and the new thing is the latest thing. And that was very expensive. So they actually just removed that, and they made that determination because they have a very write-heavy requirement. So even though the reads were slower, it was still fast enough because they could just get something by the namespace and then scan for the latest, right? They were still able to, it was a small win, or it was a small loss for reads and a huge win for writes. So I think this is kind of, again, it's an opportunity to really show your interviewer, not only do you understand databases, but you understand databases and you understand how the product requirements interact with the database layer. And this is it's a small change and a huge opportunity for, scalability. And I think that this is it's very impressive as an interviewer to see that an interviewee is thinking this way, because I think definitely more junior engineers do not think this way. They're just worried about, do they know the syntax? Can they get it right? And as a more senior engineer, you want to be thinking not only what can we do to make this better, but what can we do to make this better that's not so expensive in terms of engineering time and engineering load on our brains. And this is this is a really good example of optimizing for something because of the requirements of a product. And yeah, that's it. Here are some links I shared that I used personally to prepare for this talk. Again, I think there are so many good videos and articles that Dropbox has put out all about their system. There's so much. Like this was a pretty dense video, I think, and there's literally, I barely scratched the surface. So if you're interested, I highly recommend looking some of this stuff up on your own. Next week, we're going to talk much more about the synchronizing service and a little bit more details on some core algorithms. We'll code a little bit. And yeah, I hope you enjoyed this, and stay happy, guys. This is I think when you're doing these interviews, you have to make sure that you're interested and do whatever you have to make yourself interested. Sometimes learning more is actually the thing that helps you go farther. That's what we believe at CoderBite, at least. So have a good one, and I will see you all soon.